You ever stop and wonder how your phone actually understands what you're saying? Or how Spotify sends you perfect, crystal clear music through, what, just a bunch of ones and zeros? Well, the answer is this kind of invisible mathematical magic that is running our entire modern world. So yeah, let's get into it. We're talking about digital signal processing. And really, it all boils down to this one big question. The world we live in, with actual sound waves and light and heat, it's all analog. But our computers, our phones, none of them are. They're digital. So how on earth do you build a bridge between those two completely different worlds?
And that's the fundamental challenge, right? We're living in this analog world, but we've built these incredibly powerful digital brains to make sense of it all. Think about it. Nature is smooth, it flows, it's continuous. But computers? They're all about logic, precision. They think in separate little steps.
Here's the best way to picture the difference. An analog signal is like a really smooth ramp. You can be at any point on it, any height you want. There's an infinite number of places you could stand. But a digital signal, that's way more like a staircase. You're either on step 1, or step 2, or step 3. There's a limited, very specific number of spots you can be. So when we talk about translating our world for computers, what we're really talking about is translating signals. And a signal is just anything that carries information. The sound of my voice right now is a signal. The Wi-Fi signal reaching your device is, well, a signal. They're just patterns that hold some kind of meaning. So where does this whole journey start? How does that smooth analog wave of your voice become something a computer can actually work with? Well, the first step involves a piece of hardware called an analog to digital converter. We usually just call it an A to D converter. Its whole job is to turn that beautiful, messy wave into cold, hard numbers. And it does this translation in two really important steps. First, we take a bunch of little snapshots of the wave. That's called sampling. And then, for each of those snapshots, we assign it a number, and that's called quantization. All right, let's break these two down. Okay, so sampling. Imagine you're trying to describe the path of a race car. If you take pictures of it super fast, one after another, you get a really clear idea of its exact path, right? That's pretty much what sampling is. It measures the height of that analog wave at thousands or even millions of perfectly spaced moments every single second. But you might be wondering, how fast is fast enough? Well, this is where the absolute golden rule of digital signal processing comes in, the Nyquist theorem. And what it says is, to get a perfect digital copy, you have to take those snapshots at least twice as fast as the highest sound or frequency in the original signal. If you go any slower, you get this weird distorted mess. It's a problem called aliasing, where a high-pitched sound could end up sounding like a low-pitched one. It's a total disaster. So we've got all our snapshots. Perfect. Now for step 2, quantization. Remember that staircase analogy? Quantization is basically taking the exact measurement of each snapshot and just rounding it to the nearest step on our digital staircase. And this is where you really see the power of digital. The number of steps on that staircase depends on how many bits, the ones and zeros, we use for each sample. And here's the amazing part. For every single bit you add, you double the number of steps. And get this, that one extra bit improves the quality of the signal by about 6 decibels. That is a huge jump in clarity and accuracy, just from adding one more 1 or 0. Okay, so we've done it. We've turned our smooth analog wave into a long list of numbers. And this is where the real fun begins. Because once that signal is digital, it's just data. And now we can use pure math to change that data with perfect precision in ways that would be totally impossible in the analog world. Welcome to the digital playground. In the world of DSP, the thing that does all this math is just called a system. And you can think of it like a little black box. Our list of numbers goes in one side, the system does some kind of specific mathematical trick to them, and a brand new, changed list of numbers pops out the other side. And a lot of times, these mathematical tricks are called filters. Like a coffee filter keeps the grounds out of your coffee. A digital filter can separate different parts of our signal. It can boost certain things, cut other things, and totally reshape the information any way we want. So a really common example is something called a low-pass filter. It's just programmed to let all the low sounds, the bass, the rumble, pass right through. But it cuts down on the high-frequency sounds, like a hiss or a cymbal crash. In the real world, this is exactly what's happening when you turn up the bass knob on your stereo. You are literally applying a digital filter. All right, so we've captured our signal, we've turned it into numbers, and we've tweaked it with math. But a long list of numbers isn't something you can listen to. We can't hear numbers.
So the final step in this whole journey is to turn that processed digital information back into a real-world analog wave that we can actually hear and experience.
And this part of the process, which is done by a digital to analog converter, is basically just a very, very sophisticated game of connect the dots. It takes our series of numbers, those steps on our staircase, and uses some clever math to draw a perfectly smooth, continuous wave that passes right through them. It just recreates the analog signal.
And you know, this whole journey from an analog wave into digital numbers, through a bunch of math and back out again, it sounds complicated, but it's not slow. This is happening millions, sometimes billions of times a second inside almost every single piece of tech that you own.
And this stuff is not some abstract theory. It is everywhere. It's the tech inside your noise-canceling headphones creating an anti-noise signal. It's how your cell phone and Wi-Fi filter out all the interference. It's how an MRI machine builds a 3D image of your brain. And it's how your phone's camera instantly makes your photos look better. It is literally shaping our world.
When you get right down to it, digital signal processing is the ultimate translator. It's this incredible mathematical bridge that lets our messy, chaotic, beautiful analog world talk to the precise, logical world of computers. It's what lets one world understand and even improve the other.
And that leaves us with one last really powerful idea. The true magic of DSP is that it can digitize pretty much any signal you can measure. Sound, light, radio waves, even the signals inside our own bodies. And once they become numbers, we can reshape them however we want. So the real question isn't just about what we can do today. It's, if we can digitize and redesign reality itself, what kind of reality are we going to choose to build tomorrow?